Hi friends, I'm Shashank and we'll talk about geometric design of highways. So the content of our presentation is introduction, side distance. In this side distance there are three various kind of side distances. Then we'll talk about horizontal alignment, then vertical alignment. So starting with the introduction. In introduction, as you all know, there are different kinds of roads in India. So on the basis of functional causes, some kind of roads like expressways, national highways, state highways, major district roads, other district roads, and village roads. Now friends, we are going to talk about geometric design. So what are the various factors which are governing our geometric design? These factors are like road user characteristics, safety requirements, topography, traffic volume, design speed, vehicle characteristics, economy in construction, maintenance, aesthetically appearance too. We are going to concern about aesthetical appearance. Yes. So friends, like our main factors which are governing, all these factors are governing our geometric design. So we'll talk in details. Now guys, we will talk about the cross-sectional element of road. This is camber. So have you ever noticed the cross-section of road is in this manner? The edges have less elevation and the center part have more elevation. The center part, more elevated part, is known as a crown, and this whole thing is called as camber. Why we are providing this? The objective of this why we are providing this is cross section is provided to raise middle of road surface in transverse direction to drain off rainwater from road surface. Yes, the main thing is to drain off rainwater from road surface. But it is quite undesirable and it's not important. If we don't provide this, then what happens? Then the water will accumulate over the road and then water will go percolate to the subgrade and it affects our pavement. So we are providing this to avoid the accumulation of rainwater over our road. Okay. And one more thing, when rainwater accumulates, then the chances of slipping and skidding of vehicle also. So this is quite undesirable, but yet it is important element of our roads. Now friends, we'll talk about side distances. There are three different kind of side distances, like stopping side distance, overtaking side distance, and intermediate side distance. Why we are providing this? What its objective? What happens if we don't provide? These kinds of all questions we are going to answer. So starting with the stopping side distance. So what is the objective of providing this? Like we have a car which is moving with some design speed on a grade. Then what happens when a driver of this car see like there is an object in front of him, and the driver start thinking like, do we need to stop the vehicle or not? Is it required to apply brake or not? This is the time in which driver is thinking about the object, and this thinking of driver is based on his past experiences. Now when the driver assumes yes, he need to apply brake, otherwise I'm going to collide with the object and I'm going to die. So the driver applies brake, and when the driver applies brake, then the car starts deaccelerate, and after a certain distance it stops. So the distance between the application of brake and the stopping of vehicle, the whole distance is called the braking distance. And when the driver was thinking that do we need to apply brake or not, that distance covered by the vehicle during this time is called as the lag distance, and the time is called the reaction time. So this is provided to stop the vehicle before colliding with the object. So the concept is simple. The stopping side distance is summation of lag distance plus braking distance. We can calculate the lag distance easily by reaction time multiplying with the velocity of vehicle, because in this lag distance the driver is not applying the brake, so the distance is same as the initial distance, like initial speed, like the design speed. So this is the lag distance. Now what is the brake distance? How do we calculate? So friends, in this part we are assuming that the kinetic energy of vehicle is going to convert into the work done to stop the vehicle. So this is just our assumption. In actual practice, the kinetic energy is converted into the work done of vehicle to stop, that is friction force, and some heat evolve and some sound occurs. So the total energy is friction force plus heat plus sound energy. But in this we are going to just assume that total energy, kinetic energy of vehicle is going to convert into the friction force work done. Now by equating this we will get our braking distance. So what is our kinetic energy? It is equal to half mv square, and mass equal to weight divided by acceleration due to gravity. Now the question is how to calculate the work done. So friends, we all know that the work done is simply the force into displacement. The force is friction force plus weight of vehicle into displacement. Now how to calculate the weight of vehicle and the friction forces? Simply the weight of vehicle on grade is simple, the weight into sine theta. It's the weight component in the direction of vehicle. So friction forces in this direction, like a vehicle is moving upward, then friction force in downward direction, the weight of vehicle is also in downward direction. Then we will add the weight and friction forces, and the work done is equal to the force into displacement. Now what happens when the vehicle is moving downward? Then friction force is upwards and weight of vehicle component is in downward direction, so we will use the minus sign. Now let's calculate the braking side distance. When we equate these two, then we can calculate L. This is called as the braking distance. The stopping side distance is summation of braking distance plus lag distance. So this is our braking distance and this is our lag distance. So that was all about the stopping side distance. Let's talk about the overtaking side distance. Now friends, have you ever noticed that you have a fast moving vehicle and ahead of you there is a slow moving vehicle? You get irritated, you just want to overtake the slow moving vehicle. So what you do is just wait behind the slow moving vehicle, wait for your turn, like when you can just overtake the slow moving vehicle, and is there any fast moving vehicle coming in the opposite direction. So this all going to happen, and then you find that this is the right time to overtake. Then you what you do, you change your lane and accelerate, and you will reach ahead of the slow moving vehicle, and you stop after attaining the certain safe distance. So this is whole overtaking operation. So now let's calculate how do we calculate the distance between the fast moving vehicle, slow moving vehicle, and what is the safe distance after the overtaking operation, and what is the distance whole covered in this operation. So let's look into the phase diagram. So this is the phase 1, which is the safe distance between overtaking and overtaken vehicle before overtaking operation, and this is the phase 3. This is equal to safe distance between overtaking and overtaken vehicle after overtaking operation. So in this distance, what is happening? The driver is just looking the other lane, and is there any vehicle coming in the opposite direction? When he found yes, is there any vehicle is in opposite direction, then he don't go. When he found that there is lane clear and the vehicle is far away and it will not get affected when he took the overtaking of this vehicle, so he accelerate and reach to the initial lane and maintain the safe distance. This is the overtaking operation. So the time required to go from this point to this point is same as the time required for this slow moving vehicle from this point to this point, and the same time which is required for fast moving vehicle from moving this point to this point. Okay, so all is happening in the same time. So the safe distance is governed by this formula, which is equal to 0.7 into speed of slow moving vehicle plus 6 meters. This 6 is generally the length of vehicle. D2 is this whole distance. This is equal to 2s plus the time into velocity of this vehicle. So this is the slow moving vehicle into time, and this is also equal to the vehicle distance from here to here. So this is we can find this distance by Newton's equation of motion, which is ut plus half at square. U is its initial speed, which is equal to the slow moving vehicle, and plus half at square. So equating these two, we'll get the time, which is equal to under root 4 s by a. Now we can calculate the d2 as we know the time. So after knowing the time, we find out the d2 and d4. D4, this is called as a d4. This is the time of overtaking operation into its speed, which is the general design speed. So v naught is design speed into t. So we can calculate the d4 and d2. Now we can able to find out those overtaking side distance. Now friends, how to provide this overtaking side distance? We providing this in a zone which is called as overtaking zone. In this zone, we are providing the extra width of road so that the vehicle can overtake easily without getting affected by without getting affected from the other side vehicle which is coming in the opposite direction. So we provide the signboards here and here. This is for the starting of overtaking zone. This is for the end of overtaking zone. So the minimum distance of overtaking zone is 3 times of OSD, but it is desirable to provide 5 times of OSD. So this is all about the overtaking side distances. Now let's come on the last side distance, which is intermediate side distance. Now friends, suppose you are going on a junction. You found that there is another vehicle coming from another leg, and this is your vehicle. You see this vehicle. So what you do? You just apply a brake, and before reaching this point, you have to stop. Otherwise, your vehicle get collided with this vehicle. So this guy in the vehicle applies brake, and it reaches to this distance, and it stops. You apply brake, and you reaches to this distance, and you stop. So this is simply the stopping side distance for this vehicle, and this is stopping side distance for this vehicle. So the total side distance is intermediate side distance is SSD for this plus SSD for this. Okay, so this is about the intermediate side distance. So friends, now we'll talk about the horizontal alignment in detail. Basically, horizontal alignment is nothing but simply the straight road or a curve or transition curve. These all things are the part of horizontal alignment. Now, firstly, we'll talk about super elevation. So in this super elevation, from the figure, you can see that the increased elevation on this part of the road, and there's a decreased elevation at this part of the road, and you can also see there's extra width provided on the road. These all things are on a curve. You should notice that. Now we will talk about super elevation in detail. So why we are providing super elevation, what is its objective, and why we are increasing the elevation of a road. So friends, you must have seen, like you are sitting in a car and there is a curve occurs on a road. Then you have seen that all the passengers inside the car just go outward direction of a outward direction from the curve. Why this happen? This happens because of the centrifugal force. I know you all studied about the centrifugal force, why it happens on the curve. These are all things we have seen in the basics mechanics. Okay, so now we are considering only what its importance in our geometric design. So why we are providing this? We just want to counteract the centrifugal force acting on vehicle at circular curves. Okay. Otherwise there will be discomfort to the passengers. So the basic concept is to increase the road at the edges so the weight component of vehicle balance the centrifugal acceleration and avoid the slipping and overturning of vehicles. So in this case, we just want to balance the centrifugal force with the help of weight of vehicle. So now you can see from this figure that there is a slant of a road. This is a cross section. In this, the vehicle is running on the road. So the weight is acting downward, and the frictional forces is acting inside of the road because of the centrifugal force. This vehicle tries to go outward direction, and because of that, friction force is inside direction, and friction force is simply the coefficient of friction into the weight of vehicle, the normal weight of vehicle. So in this case, this is our weight in downward direction, and this is the normal weight component, and there is centrifugal force acting in inside direction. So by equating and balancing the term, you will get this equation. So by equating these two terms and and we are dividing the cos alpha by whole equation, then we will get tan alpha, and Fs is our coefficient of friction, V is the speed of vehicle, G is acceleration due to gravity, and R is the radius of a curvature. So in this case we are considering tan alpha is equal to E. As you can see in this graph, in this figure, this is E distance per 1 meter. So from this equation we can see that E plus F equal to V square upon G into R. We can neglect this term, or we can assume this term is equal to 1, because the E values lies in the range of 0.07 around, and Fs, as per IRC, it is said that the sliding friction is around 0.15. So this whole term is very less. So we can see that E plus F equal to V square upon GR, or we can find out the radius from this. So friends, this is all about the super elevation. Why we are providing this? Just to balance the centrifugal force, and we can provide the super elevation E value from this equation. Now come on to the extra widening. So friends, I have shown you one figure earlier, which is this figure. So you can see that this is the extra width of a road provided on the curves. So why we are providing this, we will learn in this part. So extra width of road provided because the front wheel, we know that the front wheel of a vehicle can go here and there, it can move, it can turn, but the rear wheel will not turn, it go on the straight line. So why we are providing this? Because of the front wheel and the rear wheel have different turning radius. So this is the turning radius for outer wheel, and R1 is for inner wheel. So the extra width of road which is required is equal to mechanical widening. This is equal to mechanical widening. So we are providing extra width equal to mechanical widening plus psychological widening. We are providing this psychological widening because the drivers, when he is on the curve, then he feels that his rear wheel may got off track, and he tries to get the rear wheel on the road, so he needs some extra widening. So as per IRC, the extra widening of road is equal to V upon 9.5 under root R. It is V, there is some correction required here, it is only V, and extra width equal to NL square upon 2R, N equal to number of lanes and L equal to length of vehicle. It depends on the length of vehicle, and R is the radius. So this is all about the extra widening. We are providing this to us accommodate the rear wheel on the road, which is equal to mechanical widening plus psychological widening. Now let's talk about transition curves. So friends, why we are providing transition curves? Let's assume that we are not providing transition curves. So what happens? We join two straight roads with this circular curve. When vehicles come on the curve, then we can see that the straight road have a radius equal to infinity, and the circular curve have radius equal to say RC, and the vehicles come on the curve, then push, the vehicle overtopple, or the vehicle slide away, or the passenger inside the vehicle feel the discomfort because of the jerk, because of centrifugal forces. So this may all happen if the straight road is directly connected to a circular curve. And one more thing, and we are providing extra widening on the curves, then it may look like this. It is not aesthetically good. So this, to compensate all these things, we are providing transition curves. Now we are designing transition curves for the three different criteria, which is comfort of a passenger, second, introduction of super elevation, third, minimum length as per IRC. This is the minimum length required for transition curves as governed by the IRC codes. So first of all, we'll talk about transition curves as per comfort criteria. So we are providing comfort to the passengers so that the passenger will not feel any jerk because of the centrifugal force. So we are doing nothing. We are just providing the gradual introduction of centrifugal force so that the passenger will not feel the sudden jerk, sudden force. Otherwise, there's a discomfort feeling in the passenger. So in this case, centrifugal force is so acting that the sense of jerk for passenger is not causing discomfort, where jerk is defined as the rate of change of acceleration. Now, we can derive that the change in acceleration equal to change in acceleration is equal to v upon t. Then we can derive from the t equal to something. Then from the direct result is length of transition curve equal to vq upon rc, where c is rate of change of acceleration, c equal to 80 upon 75 plus v, which is given in the IRC code, where v is in kilometer per hour and all the units in this is in SI. So the length of transition curves on the basis of introduction of super elevation. Now, if we provide a sudden introduction of super elevation, we can see that there is a straight road and we provide the higher elevation, then it may cause anything like a vehicle may overtopple because of the certain introduction of super elevation. So we are providing the gradual introduction of super elevation in this transition curve. This is the gradual introduction of super elevation. This is the rate of change of introduction of super elevation. You can see this triangle is basically the rate of change of introduction of super elevation, which is n in our case. Then the length of transition curve equal to L equal to E into N W plus WE. This is our extra widening. We are providing this extra width on the curve, so we are considering in length of transition curve. We are providing L for this for rotation of road about the inner edge, and L equal to this for rotation of road about the center line. You can see that we are rotating our road about center line. In this case, we can also rotate our road about the inner edge. In that case, then in the case of rotation of road about the inner edge, our length will be this and this much. IRC providing two different introduction of rate of super elevation. For plain terrain it is equal to 150:1, and for rolling terrain it's 60:1. Now, as per IRC, the minimum length of transition curve is given as L equal to 2.7 v square by r. This is for plain and rolling terrains, and the L equal to v square upon r for hilly and mountainous terrain. These two different length of curves are governed by the IRC. So guys, there are several curves which we can provide for our transition curves, like spiral, cubic parabola, Lyman skate, square parabola. Like we can see here, this is our Lyman skate, Bernoulli Lyman skate. This is our spiral curve. This is our cubic parabola curve. So cubic parabola is generally provided in railways, and spiral curves are best in highways. So these shapes are governed on the basis of the deflection angles of a connecting roads. So this is about the transition curves, and now let's come on the vertical alignment. So friends, what is vertical alignment? Simple. It is happens when there is hills and valleys comes on our straight roads. So we have to connect two different grades, and there we provide some certain geometrical designs, like we provide some summit curves, valley curves. These are the curves, and these all the things are related to the vertical alignment. So let's look into details. So friends, what is summit curve? So this happens when two different grades of road join with smooth vertical curve. So there are four different conditions in which we can provide summit curves. Like first, when this rising gradient meets a steep rising gradient, then we have to provide this summit curve. When the rising gradient meets horizontal curve, then we have to provide this summit curve. When a rising curve meets decreasing curve, then we provide this summit curve, and when the straight or a decreasing curve meets more steep decreasing grade, then we provide this summit curve. These are the circumstances of providing summit curves. Now, what are the circumstances and what is our design criteria of summit curves? So basically concept is same, like we don't want an accident on the roads, and the general concept is we are designing summit curves on the basis of the side distance. So while this car is on the curve and it is saying that another vehicle is on the curve also, then this vehicle must have a side distance which is equal to stopping side distance. So this is our designing criteria. And on this curve you can say that on the curve there is a centrifugal force and there is chance of discomfort, but on summit curve centrifugal force acting outwards and the spring of vehicle is not compressed. There is a shock ups and the springs which is not compressed, and therefore passenger comfort is not an issue. So the design of summit curve as a square parabola, because the rate of change of slope is decreasing always, so more side distance available on the top curve. You can see that we provide this curve as a parabola. So on the top of the curve there is a more side distance available as compared to the on this downward and this in this part of a road. We can also provide a circular curve as summit curve, because the side distance available is always constant. Now we are providing this as a square parabola, so the equation of a square parabola is y equal to nx square upon 2l. X is a distance from the origin. We are considering our origin here, and this is y. We are going x, then this is y. We are going x, then this is y. So we are putting this y is equal to h, then x equal to s1, and y is equal to small h, then x equal to s2. So our total stopping side distance is equal to s1 plus s2, which is equal to s, and h and small h, these are the two heights. You can see from here this capital H is equal to 1.2 meter around, and this is small h equal to 0.15 meters. So by considering this equation, when this equation comes when the stopping side distance is smaller than the length of curve, because we are considering this stopping side distance on the curve. So this equation is valid when the stopping side distance length is less than the length of curve, which is L equal to n square upon 2 under root h plus under root small h. When the side distance is more than the length of curve, then our equations turns out to be 2s minus 2 at capital root h plus capital small root h divided by n. N is equal to n1 plus n2. This is summation algebraically. So this is the small h and capital H values. This is for summit curves. Now comes on the valley curves. So as we have seen in the summit curve, we are providing for the 4 different conditions. Here in the valley curve we have the similar 4 kinds of conditions, like when the steeper gradient meets less steeper gradient, when the steeper gradient meets horizontal gradient, when the decreasing gradient meets rising gradient, when the increasing gradient meets more increasing gradient. Then the shapes of curve is valley curve. So what is the concept of valley curve? As we have seen that in the daytime there is no problem of any side distance, because this vehicle can see this vehicle at any distance on a curve, on a valley curve. Okay, so in daytime there is no such kind of problem. Okay, but in nighttime what happens, like overtaking side distance is not a problem in nighttime, because the tail light is always available for this vehicle, so overtaking is not a problem. But if there is some object here, and the headlight can see up to this distance. So this distance should be equal to stopping sight distance. Alright, otherwise the vehicle may hit the object in the night. And there's another design consideration is the comfort criteria, because the radius of curve will be somewhere here, and because of this the centrifugal force is acting downward here, here, here and here, and because of that the spring always remains compressed, and when there is some impact comes, then the spring will not have sufficient compression, because there will be discomfort and discomfort to the passengers. So there are two conditions for the designing of valley curves. First is sight distance, second is comfort criteria. We must also take care about the drainage, because in the valley there are the chances of accumulation of water in the rainy season. So the consideration of valley curves are, we are providing two transitional curves. First one is here, then another one is here. Because of that the straight road and this radius, the straight meets circular radius r, then r go to the straight road of radius infinity. So there will be no problem of discomfort on the transition curves. So length of transition curves we can provide on the basis of comfort criteria. We are providing this transition curve as cubic parabola. So the equation is y equal to 2n upon 3l square into x cube. Now on the basis of comfort criteria we can find out the length of transition curve equal to L equal to under root n into v cube upon c. This is the same c as we have seen in the super elevation cases, or in the transition curve cases. C is equal to 80 upon 75 plus v. So this is for the comfort condition. Now let's come on the case where we are designing the length of curve on the basis of headlight sight distance. So this is our vehicle having headlight at distance h1 from the road. This is its horizontal line, and the beam of light is at angle equal to alpha. So this is our stopping sight distance s. This is equal to s tan alpha, and this is our height h1 plus s tan alpha, and this is s. So now put on the equation, when the length of curve is more than the stopping sight distance, you can see that this is our length of curve and stopping sight distance is simply up to this much. Then here we can find out the length. When the length of curve is less than the stopping sight distance, then we can find the length from equating these two equations, where beta is our beam angle, h1 is the height of flight from ground. So friends, this is all about the vertical alignment, and we are completing whole geometric design process. Thank you very much. I am Shashank.